All right, Chem 1110 students, we are to the last video in Chapter 2, and here we're going to talk about how we um, deal with elements or molecules, atoms, in terms of problems and even just trying to handle them because they're so small. So what we use is a counting number called the mole. It's the same thing as talking about a dozen bananas or a dozen eggs. It's just that atoms are so very small that the mole is a very, very large number. It is defined as the amount of a substance that contains as many little pieces, elementary entities, as there are atoms in exactly 12 grams of carbon 12. So we're back to that definition we've used before. This number can be experimentally determined, and I think that's actually a lab we're going to do this semester. Avogadro's number is 6.022 times 10 to the 23rd. Typically, we would just round it off as 6.022 times 10 to the 23rd. So 1 mole is 6.022 times 10 to the 23rd particles, just like a dozen is 12 eggs or bananas, and a gross of pencils is 144 pencils. It's just a very large number in order to get a large enough amount that we can handle. And here's a picture of what a mole of various substances look like. You know, you've got so many milliliters of water, a balloon full of helium, sugar, salt, copper, etc. And you can see those and you can handle those. And in order to do that, we have to look at a very large number of those particles, and that's what a mole is. So there's all kinds of problems you could do with a mole. Calcium is the most abundant metal in a human body, obviously because of the bones. Roughly, a human body contains 30 moles of calcium. So it's determine the number of calcium atoms in 30 moles and the number of moles of calcium in a sample containing 1 times 10 to the 20th calcium atoms. So here we want to get used to it in dimensional analysis. We're going to use Avogadro's number, and it's pretty straightforward. If you have 30 moles of calcium, the amount that's typically in a human body, you use Avogadro's number as atoms per mole so that the moles cancel and you're left with an answer in atoms. In the other example, we want to know how many moles there were in 10 to the 20th atoms. And so here we use that equivalency, that definition of a mole in terms of Avogadro's number. We flip it over so atoms cancel and we get our answer in moles. So molar mass of a substance is the mass in grams of 1 mole of that substance. And once again, molar mass is extremely important in terms of giving us an amount that we can deal with. 12 grams of calcium, you can see. 18 grams of water, you can measure out. So that's what a molar mass is all about. And once again, it's a mass of a mole of carbon 12, so it's exactly 12 grams. If you have the 1 carbon 12, that's, the mass of 1 atom is 12 AMU. The mass of a mole is 12 grams. And, the molar mass specifies the mass of 1 mole so that we're in grams. We usually denote it as grams per mole because this helps us cancel our units when we're doing dimensional analysis. So I have another example here. You'll notice my cancellation marks are on the slide, and I apologize. I just obviously didn't remove them. So the first thing is determine the number of moles of carbon in 25 grams of carbon. The next one is the number of moles of helium in 10.5 grams of helium. The last one is how many moles are in 15.75 grams of sodium. And so the thing that we have to realize is we're going to use the average atomic mass as a molar mass, because if you just have a sample of sodium that you dig out of the ground or you get out of the storeroom, it's going to have that isotopic abundance, that natural isotopic abundance, and the average atomic mass takes that into account. So that's what you'll use to convert from mass to moles. So once again, we know what the setup is. We're going to use the molar mass of carbon as 12.01. You can find that on a periodic table. Helium is 4.003 grams per mole. Sodium is 22.99 grams per mole. And so you fill them in, you flip that equivalency of a mole and 12.01 grams so that your grams cancel, you get moles of carbon. Or in the case of helium, it's that average atomic mass of 4.003. And in the last one, you're using that average atomic mass for sodium. Okay, then we have this one where we're trying to determine the number of atoms of carbon in a particular mass of carbon. And then what's the mass that contains a certain number of atoms. And so once again, we're going to use those conversions, the 12.01 average atomic mass for carbon and the 6.089 times 10 to the 18th, and the molar mass of helium as being that average atomic mass of 4.003, and you need Avogadro's number. So once again, dimensional analysis, you're going from 0.515 grams of carbon and you're trying to get to atoms. And so use the molar mass to go from grams to moles, and then Avogadro's number to go from moles to number of atoms. And you can see you do it so that your units cancel and you're left with carbon atoms. In the helium example, you're starting with atoms and you want to get grams, and so you use Avogadro's number to get you to moles, and then the average atomic mass to go from grams to moles. So basically, molar mass is just a conversion factor from mass to moles and vice versa. Avogadro's number converts from moles to atom, and there's a little graphic here that you might find useful. And that's it for chapter 2.